Okay, so the next speaker
Yes.
for today is Joshua Wrigley, and he will talk about topological groupoids for classifying toposes. Whenever you're ready.
Thank you very much for the introduction. Thank you for coming. I apologize to anyone who was at CT, because this is going to be a bit of a rehash of my CT talk, but there's going to be some new things in there as well with the time limit that this format affords. So what is the idea of representing classifying toposes by topological groupoids? It's coming from this observation that theories, I mean, this is most naturally seen in a propositional case, but theories can be represented by topological structures. And when we generalize to the first order setting, we see that it's really groupoids of models with topological structures which can represent theories. And if we're able to represent a theory, I mean, this will be made formal in a sec, but if we're able to represent a theory by a groupoid of models, we should be intuitively thinking that that means the groupoid of models contains enough information to represent a theory. And the natural question is, when is this possible? When do we have such structure on a groupoid of models? And the characterization I want to be talking about today is this one, that a groupoid of models can represent a geometric theory if and only if we have these two conditions. Firstly, the groupoid is conservative, and secondly, that it eliminates parameters. So in the overview of the talk is as followed, and it's nice and color-coded. So we're going to put formal meaning to this vague sense of being represented by a topological structure. To do that, we're going to talk about classifying topos theory, which is going to be the logical side of our representation. And we're going to talk about toposes of sheaves on a topological groupoid, and that's going to be our topological structure side. And we're going to say that something is represented by something else if they're equivalent as toposes. We're going to review an example of a representing groupoid in order to then introduce the idea of elimination of parameters. So that's the third part. We're going to define what it means to eliminate parameters. In the fourth part, we're going to then technically restate the main theorem with all of the knowledge of the previous sections and give a formal statement of what I mean by this vague statement here on the first slide. And we're also going to sketch briefly some of the ideas, the provenance of this idea of elimination of parameters. And then finally, we're going to look at how we can apply this classification result in order to deduce many examples of representing groupoids for theories. So let's begin with part one. So we're going to start talking about the topological structure side of this representation. So the fundamental structure we're going to be considering is a topological groupoid. So a groupoid internal to the category of topological spaces, a diagram of this form satisfying the obvious equations, where we endow everything with topologies, and these maps are all continuous with respect to those topologies. And we're going to say that a groupoid is open if either the source or equivalently the target map is an open map as well. Once we've got a topological groupoid, we can represent it as a topos this way. So once we've got a groupoid, a bundle on that groupoid is going to consist of a map from a set Y living over our set of objects. And it's going to be equipped with an action by the set of arrows of our groupoid, which basically means that for every arrow in our set of morphisms, there is a connection between the fibers of our map Q. And when we include all of the topologies into this equation, we're going to say that such a bundle is going to be a sheaf if the map Q is a local homeomorphism, and if the map beta is a continuous map, if it's continuous with respect to the appropriate topologies. A map between sheaves is going to be a continuous map of sheaves, so that is satisfying this triangle equation. And the map also has to be equivariant with respect to the actions we're endowing on our sheaves, which is that this square commutes. And when we take those objects and these morphisms together, we actually get a Grothendieck topos, which we're going to call the topos of equivariant sheaves on our groupoid. So that is the topological side of our representation, that for every topological groupoid, we can get a topos this way. Let's talk about the logical side next. And the notion we're going to use is a classifying topos. So toposes generalize topological spaces. And in that sense, a classifying topos is the generalized space whose points are models of a theory. So more concretely, that means that for a theory, we have this equivalence between the models of our theory and the points of our topos as geometric morphisms. And of course, we can remove any reference to sets and talk about generalized points and models of our theory T in any topos. And this defines our classifying topos up to equivalence. And of course, every geometric theory has a classifying topos, and every topos is the classifying topos of some theory. So our classification result for the topological representation of a classifying topos is going to suffice to talk about representation of all Grothendieck toposes. And so this gives us the logical side of our correspondence, and we're going to say that a open topological groupoid represents a theory T if and only if we have an equivalence of the respective sheaf topos and the classifying topos. So let's have a look at one such example of a representing groupoid. If we had a theory whose set-based models were conservative, we would expect, given this rather vague notion that representing groupoids are ones which contain all of the information of the theory, that if we took the groupoid of all models, this should represent our theory T. But we run into size issues because, of course, a theory can have unboundedly large models. So we can get around this by considering a suitably large set of models. And this is where the idea of an indexed model comes in. So if we've got a structure over a signature, we're going to say that it's indexed by a set of parameters K if there is some subset of that set of parameters, and an expansion of our model to the signature where we've added a constant symbol for every parameter in the subset, such that M now satisfies this sequent here, which says that every element in our model is the interpretation of some parameter. So we're interpreting not necessarily all of our parameters. Yes, not necessarily all our parameters, but everything in our model is the interpretation of some parameter. And of course, this is equivalent to a choice of partial surjection for our model. And if we take the groupoid of all K-index models of our theory and all isomorphisms between these, then we get a representing groupoid we can endow this groupoid with some suitable topologies and get an equivalence between the sheaves on that groupoid and our classifying topos if and only if the k-indexed models are conservative. That is, that if any two formula interpreted identically in all of our k-indexed models, then they have to be provably equivalent in our theory T. And so this suffices to show that any topos who, with enough points, can be represented by a topological groupoid, and an open topological groupoid, in fact. But this is just one example among many. And in the following sections, we're going to develop our characterization of all of the open topological representing groupoids. So the key idea is elimination of parameters. To do that, we're going to need to generalize the notion of definable. So if we have a model, then a definable is just going to be the set of elements which satisfy a formula. And if we've got an indexing of our model, we can also consider definables with respect to some parameters. So that is that all of the elements which satisfy a formula where that formula contains parameters. And we can do the same whenever we have a groupoid of models. What we're going, all the generalization does is that it just takes the subset of the co-product over all of the models, and we take the definable to be the subset of pairs considered as a subset of a co-product of the element and the model, such that the element satisfies the formula with or without parameters in said model. Now, each definable, for every n, and here we're considering a single sorted theory for simplicity, but this is quite easily generalized. For every n, whenever we have a definable subset, we get a subset of this bundle. This bundle is where the fibers are the n tuples of our models. And we get a subset of just those n tuples which satisfy our formula. And we can quite clearly see that because any isomorphism between our models preserves the interpretation of our formula phi, then this subset is actually what we call stable under the x1 action. That the image of anything in our subset under the action of x1 is still contained in our definable subset. So, of course, isn't the case when we talk about definables with parameters. That's because an isomorphism between our models doesn't necessarily have to preserve the additional structure of the parameters. They don't have to preserve the interpretation of the parameters. They, in fact, while the parameter m might not even be interpreted at all in the target of one of these isomorphisms. So definables with parameters are not stable under the action of the groupoid on this bundle. But of course, we could consider taking the closure under the x1 action, taking the orbit of a definable with parameters, and to get a subset which is closed under the action. And look, in this example that I've written up here, the closure is actually equal to the interpretation of phi from a previous slide. And that's precisely what we mean by elimination of parameters. That when we have an indexing of our groupoid by some parameters, that groupoid eliminates the parameters if there exists some geometric formula such that the orbit of any definable with parameters is definable without parameters. I will just add as well that actually we don't need to check this for every formula. It suffices to just check that the orbit of the formula y equals some tuple of parameters is definable without parameters. Okay, so that can conclude what we mean by elimination of parameters, and now we can state the classification result. which is that if we have a geometric theory and some small groupoid of its models, then that groupoid can be endowed with topologies, making it an open topological groupoid, for which there is an equivalence between the sheaves on that topological groupoid and the classifying topos of the theory, if and only if we have these two conditions. That firstly, our groupoid is conservative. As mentioned before, this means that if the interpretation of any two formulas are identical, then this implies that the formulas were in fact provably equivalent in the first place. And the second condition is that for there exists an indexing of the models in our groupoid by a set of parameters for which the groupoid then eliminates those parameters. I want to give a little bit of a sketch of where these ideas come from, because at least from my point of view, the ideas are quite simple, though I appreciate that what I'm going to say next might not be followable for everyone. So we'll go through and then we can decide whether I've aimed this too high or not. So we're only going to show, or rather sketch, one direction, which is that there is a choice of topologies on our groupoid such that we have this equivalence. Now, the first step is to find an indexing of our groupoid. Now, under this equivalence between the sheaves on our topological groupoid and the classifying topos, this formula in the universal model inside the classifying topos is going to be identified with the sheaf we saw earlier, which is that the fibers of the sheaf are going to be the end tuples of our models. And because this is sheaves on a topological groupoid, this projection map down to the models is a local homeomorphism. So in particular, that means that the images of the local sections of this map with open image is jointly surjective. And so we can index the elements of our model by the local section of this local homeomorphism, and we index it by the name of the local section. And this gives an indexing of our model, and it's very nicely behaved. So that gives us the indexing. The second step is to then start considering sub-objects of this sheaf in the category of sheaves on the topological groupoid. Oh, what have I done here? Are you going to let me? Apologies. Okay, it's working now. We can continue. Hey. I'm assuming you want to see my face, which is why I'm slightly annoyed that the video keeps on cutting on and off. Can everyone hear me, see me, and the slides?
I can hear you, and I see the slides with no lag perfectly.
Okay, then we need no more. Okay, so this gives us an indexing of the elements of our model, and that's the first step to find the indexing. Now, the second step is to just recognize that the sub-objects of this sheaf are the stable open subsets of our space. Now, in particular, we have two examples. So I haven't argued about why we've already seen that the interpretation of a formula without parameters is stable. We haven't seen that it's open, but that comes from the fact that we have an equivalence here. And the other aspect is that because this is an open topological groupoid, then this open image of a local section, it's an open subset of our space. And so when we take the orbit of it, when we take the closure under the x1 action, because it's an open topological groupoid, this remains open as well. And so the orbit of x equals m is also a stable open subset of our sheaf and therefore a subobject. And finally, the next step in order to get to conservativity and elimination of parameters is to study this map, which is the map from the subobjects in the classifying topos of this formula to the subsheaves of our sheaf in the topos of sheaves. And this map sends a formula and a universal model to its interpretation in the groupoid. And we can see quite easily that this map is injective if and only if the groupoid is conservative. And with a little bit of effort, we can also deduce that it's surjective if and only if the groupoid eliminates parameters. So that's where our two conditions are coming from, that conservativity corresponds to the injectivity of this map on subobjects, and surjectivity corresponds to elimination of parameters. Okay, so hopefully we've got a bit of appreciation of where the two conditions are coming from. And now I want to talk a bit more concretely about certain examples. So over the next few examples, one of my goals is to argue that the previous results found in the literature are covered by this classification result. And I also want to talk about some examples which weren't in the literature beforehand, but perhaps are a little bit easy to deduce. And I also want to explain the difference between topological representing groupoids and localic representing groupoids in the style of Joao Tierney, De Boek, and others. Okay, so firstly, we saw that the k-indexed models, the groupoid of k-indexed models, is a representing groupoid whenever those indexed models are conservative. And that follows because we can fairly easily show that the groupoid of k-indexed models eliminates parameters. And the same argument also suffices to show that the groupoid of enumerated models, so that's where every element of our model is indexed by infinitely many parameters. This is the type of groupoid considered in the original Books and Mordyke paper. We can show that groupoid also eliminates parameters. What formula is eliminating the parameters? Well, it's this one. So whenever we have a tuple of parameters, we consider its closure, its stabilization, and we see that it's interpreted by the formula which expresses which elements of the tuple of parameters were equivalent. So slightly related is this version. So this is quite an algebraic version and sort of serves as an example of why the terminology elimination of parameters kind of makes sense if you're used to eliminating parameters from equations. So we're going to say that the theory of algebraic extensions of some chosen field K is the theory where the axioms are the standard axioms of a field. We're going to include in our signature a constant symbol for every element of K and axioms so that those constant symbols interpret a copy of K inside any model. And we're going to include this axiom, which expresses that any model is algebraic. It's an algebraic extension of the interpretation of K inside that model. So this is our theory. What's our groupoid? We're going to take the groupoid of all intermediate extensions between the field K and its algebraic closure and all isomorphisms between these. We can easily make this an indexed groupoid. We can index it, the elements of an intermediate extension, just by considering it as a subset of the algebraic extension and labeling the elements accordingly. When we do this, we see that this index group eliminates parameters. It's obviously conservative. And so we end up with this equivalence, that this theory of algebraic extensions is represented by the groupoid of all intermediate extensions. And the formula which eliminates parameters, so for any tuple of parameters, which is to say elements in the algebraic closure of K, then this formula here corresponds to the orbit of x equals n. So here, each qi is the minimal polynomial over some extension by all of the other elements of our tuple. The idea behind this formula is that the automorphism group of the algebraic closure of K acts transitively on the roots of irreducible polynomials. That's where we get this elimination of parameters from. Okay, so that's an example of something which feels kind of like the groupoids we considered on the previous slide, but here we've got a different formula eliminating the parameters, and so we wouldn't have been able to find this groupoid with the previous methods. The next examples I want to talk about come from topological Galois theory in the sense of Caramello. So a theory is said to be atomic if every model theoretic type, so we heard earlier talk about type theoretic types, these are types in the model theoretic sense. So a theory is atomic if and only if every type is isolated. What does that mean? That means that for each for each tuple of elements in our model, there is a formula which expresses the fact, which isolates the type of n, that is, well, firstly, n satisfies that formula. And for any other tuple in our model, we can show that n prime satisfies all of the same formulae as n, if and only if n prime satisfies a single formula, chi-n. And so that's what we mean by an atomic theory. An ultra-homogeneous model is one in which every partial isomorphism of finite substructures of our model extends to a total automorphism of our model. And then we can confirm the result of Caramello, which is that we have that a model of an atomic theory, its automorphism group eliminates parameters if and only if that model is ultra-homogeneous. And we see that that is the case, that if M is an ultra-homogeneous model, then the formula eliminating parameters for this formula is precisely the formula chi that should be a chi subscript m for the parameters m. And hence we conclude that the classifying topos of an atomic theory is equivalent to this is B aut of M. So here we're equipping the automorphisms of our model with a certain topology, and this is the topos of continuous actions by that topological groupoid on discrete sets. And we get this equivalence if and only if M is a conservative and ultra-homogeneous model. And that's just by applying the classification result as well. Let's go even more concrete. Let's consider a particular example of a atomic theory, the theory of dense linear orders without endpoints. So these are the axioms of our theory. Here's the equation expressing denseness and then the lack of endpoints. And we see that the rationals with the usual order is an ultra-homogeneous model of the theory. It's also conservative. And hence, we have, I think, a fairly well-known result that the classifying topos of dense linear orders is equivalent to the continuous actions by the topological automorphism group of Q. So that's an example of an ultra-homogeneous model, but quite interestingly, we also have some fairly simple examples of dense linear orders without endpoints, which aren't ultra-homogeneous. So here, let's consider this model, R plus R, which is where we take two copies of R and give them a lexicographic order. This is a dense linear order without endpoints, quite clearly, but it's not an ultra-homogeneous model. To see why, if we have anything in the first copy of R and map it to the second copy of R, this is a partial isomorphism. It's a partial isomorphism because there's only a single one type for dense linear orders. But it cannot be extended to a total automorphism of R plus R. The reason being that the down segment here of this model is Dedekind complete, but the down segment here is not Dedekind complete. It has a gap here. So this is a model which is a dense linear order, but it's not ultra homogeneous. And so therefore we have that the classifying topos is not equivalent to the continuous actions of its automorphism group. Now, I know that I'm running a little bit over time, but I just want to sort of sit and stress this point a little bit, that this is very different to what we expect to see in the localic case. And this is a counterexample to one of the questions I got by Steve Audi at CT. So we know by the theory of Joyal-Tierney and de Book that the classifying topos of dense linear orders is equivalent to the continuous actions by the localic group of automorphisms of R plus R. And so this expresses the difference in flavor between localic representations of classifying toposes and topological representations of classifying toposes. The issue here is that this group is not a spatial group. And so that's where this difference between this group classifying, this group representing the theory and this topological group not representing the theory. I will end here, just skipping over the last slide. Be sure to ask me about it in questions and we can go over it. Thank you very much for listening.
Thanks to you. Thanks for the talk. I guess if there are any questions, you can ask freely, unmute yourself and go. Millie, is that you?
Thank you very much. And no, it's just that I enjoyed the talk. Thank you very much. I will need more time to learn about it. Thank you.
Thank you very much, Millie.
Hi, Josh. I have quite a naive question, actually. I was wondering if you're aware of any connection between the elimination of parameters and the elimination of imaginary elements.
This is a good question. And certainly elimination of imaginaries motivated the definition I used for elimination of parameters. Specifically, if you look at I forget the name of the paper because it's in French, but Bruno Poisat has a paper where he talks about elimination of imaginaries in the model theoretic sense. And I tried to sort of see if there would be an equivalence between the two. And as far as I can tell, there isn't, neither is a special case of one or the other. They look very similar, and that was the inspiration for the name, but no, as far as I can tell, there isn't like a deliberate connection between the two.
Aha, I see. Okay, thank you.
Thanks for the question.
And I have a question, general question, about the meta theory. Are these results classical or can be done also constructively? Is a meta theoretic, apart from a size issue?
This is another good question. we do use certainly decidability. Decidability of sets comes into it. And there might be one or two times where you have to use choice as well. So no, this is very much living in the sort of classical set theoretic universe. But what I was aiming at to try and create a dialogue with traditional model theorists initially, but no, certainly working out how this generalizes to the constructive setting would be very interesting as well.
Thank you very much.
Good. Any other question?
Perhaps if there's no more questions, I could do as Steve did and go over the last slide.
Yeah, of course.
Cool. Okay. So let's reset where the story was, and we were talking about how the automorphism group of R plus R doesn't classify, it doesn't represent our theory of dense linear orders. But of course, it's a Grothendieck topos, it has to classify some theory. And using the results of elimination of parameters, it can be relatively easy to recognize what the theory should be. So if we look at the automorphism group, we notice that if we start off with something in the first copy of R and we look at its orbit, we don't get anything that's definable. We get the first copy of R, it acts transitively on the first copy of R, but we don't get anything that's definable without parameters. And similarly, if we start off with anything in the second copy of R, it acts transitively on that second copy, but this is also not definable without parameters. And so we are motivated to introduce some predicates which get interpreted as I am the first copy of R and I am the second copy of R. And it turns out that if you introduce these predicates to the signature, then the automorphism group of R plus R now eliminates parameters over this expanded signature. And so immediately by the classification result, we're able to recognize that this topos classifies the theory of the model R plus R, but now rather than just being a structure over the signature of a linear order, it's now a structure over the signature of a linear order and two unary predicate symbols. And we could call this theory the theory of generic Dedekind cuts. So this is the theory of Dedekind cuts from the usual notion of how you define real numbers, but we're doing this over an arbitrary dense linear order. And so if I can pontificate a little bit at the moment, when I started coming up with these results and started presenting it to people and at conferences, quite often people will come up with like, oh, this is my favorite theory. Here's a theory. Can you tell me a nice, interesting groupoid that represents this theory? And anecdotally, at least, I found it quite difficult to work in that direction, to go from a theory and find some interesting groupoid that represents that theory. But it's using the classification result, it's much easier to go in the other way, that you start off with a groupoid of structures and then finding a theory that groupoid of structures satisfies, because you just need to expand the signature so that all of your orbits of parameters are definable, and then just look at all of the sequence which is satisfied by those models, which is precisely how you come up with this theory of generic Dedekind cuts. So yes, maybe there'll be more questions, but I thought that was cool.
Thank you. if someone wants to ask additional questions, feel free. Apparently not. So, Joshua, thanks again for your nice talk, and thanks for being with us.
Thank you.
I guess now whoever wants to stay for a while can. The room is open.